Hello friends, welcome back. In this video, I will be focusing on the reactions of carbohydrate that are the osazone formation, rough degradation and the Kiliani-Fischer synthesis. So let's start with the first, that is the osazone formation. So first of all, what is the osazone? Suppose if we prepared a compound in our laboratory, then to confirm this product, we can prepare the derivative of the same. And as we come across the synthesis of carbohydrate, then after the formation of this carbohydrate, if we confirm the product, then we can also prepare the derivative of this carbohydrate, and the osazone is one of the derivative of carbohydrate. So you can define the aldose and ketose react with one equivalent of phenylhydrazine to produce the phenylhydrazone. In contrast, both the C1 and C2 react with the three equivalents of phenylhydrazine to form a bishydrazone known as the osazone. That means initially we have our carbohydrate, and if we react this carbohydrate or a sugar molecule with a phenylhydrazine. Okay. So phenylhydrazine means what? The pH NH2. Okay, this is the phenylhydrazine. Then this phenylhydrazine is react with the aldehydic molecule of our carbohydrate. Okay, so initially the one equivalent is reacted with the aldehyde of our carbohydrate unit. Okay, then after there is a removal of aniline, there is a formation of another carbonyl group at C2 position. Okay. Then after the formation of this C2 carbonyl, there is a hydrolysis, and after the removal of water molecule, we got at carbon number 1, there is a aldehydic group. And after the formation, once there is a form aldehyde molecule, then another two equivalents of phenylhydrazine can be react, and we got the osazone as a product. That means the aldose and ketose react with one equivalent of phenylhydrazine to produce the phenylhydrazone. That means when we react the phenylhydrazine with aldose or ketose, it gives the phenylhydrazone. Okay. In contrast, both the C1 and C2 react with, initially we react one equivalent of phenylhydrazine with the aldoses, it gives the phenylhydrazone. Okay. But if we react the three equivalent of phenylhydrazine, then it gives osazone as a product. So how it can be formed? Let's see. This is the aldose molecule. Okay, carbohydrate sugar. This is the aldose. Okay, why it is aldose? Because here it is a aldehydic group, therefore it is called aldose, and or this is the ketose molecule. Okay, so if we react three equivalents of phenylhydrazine, then it gives osazone as a product, and this is the structure for the osazone. Okay, and these are the byproduct. This is the aniline NH3 and water molecule. These are the byproduct. This is the simple reaction. Initially, the one equivalent of phenylhydrazine is react with this aldehydic molecule. Okay, in a mechanism, the one equivalent of phenylhydrazine will react with aldehyde. It gives in first step there is a phenylhydrazone, and after the formation of phenylhydrazone, this hydrogen can be abstract, and here it is a formation of double bond. Initially here it is a phenylhydrazone. Okay, in first step after the reaction of phenylhydrazine, we got the phenylhydrazone. Okay, and after the phenylhydrazone, here there is a abstraction of this proton, and there is a formation of double bond. Okay, and once there is a formed double bond, here it is a tautomerization, and we got carbonyl at this C2 carbon atom. Okay, in next step we got the carbonyl group, and after the formation of this carbonyl, there is a hydrolysis, and after the hydrolysis we got here it is a OH, and this is a OH. This phenyl hydrogen converted after the hydrolysis, this convert into OH, and here this carbonyl converted into the OH group. Okay, and after the removal of water molecule, we got aldehyde as a product. That means in first step we got the phenyl hydrogen, then by the removal of what aniline, And the hydrolysis, we got in first carbon atom the aldehyde group, and the second carbon atom there is a ketonic group, and once it form, again we react two equivalents of phenylhydrazine to got the osazone as a product, and this osazone is a derivative of the carbohydrate which can be conformed. Okay. So the configuration at C1 and C2 is lost in the formation of osazone. The C2 epimers form identical osazones. For example, the D-glucose and the D-iodose are the C2 epimers. Both form the same osazone. That means the C1 and C2 is lost in the formation of osazone. The configuration initially, if we take two different aldoses, okay, but after the formation of osazone, they lost their configuration at C1 and C2 carbon atom. Therefore, the C2 epimers forms the identical osazone. For example, the D-glucose and the D-iodose are the C2 epimers and both forms the same osazone. You can see the structure. This is the structure for D-glucose, and when it is reacted with three equivalents of phenylhydrazine, then it forms the osazone as like this. Okay. And here we have a D-iodose, and when D-iodose is reacted with three equivalents of phenylhydrazine in catalytic H+, then also we got same osazone. That means the C2 epimer gives same osazone because this C1 and C2 has lost the configuration in the formation of osazone, and the remaining moiety is same in the iodose and D-glucose, therefore they gives the same osazone. Again, the ketose reacts with the phenylhydrazine at C1 and C2 position to form the osazone. The D-glucose and the D-fructose form the same osazone. Again, the D-glucose and the D-fructose form the same osazone. Here you can see the D-glucose structure, and when it is reacted with the three equivalents of phenylhydrazine, it gives this type of osazone. Again, here we have a D-fructose where the structure for the D-fructose is different, but when it is reacted with the three equivalents of phenylhydrazine, this also gives the same osazone. Okay. Our next reaction is the rough degradation. The aldose chain is shortened by oxidizing the aldehyde to COH, then the decarboxylation. That means initially we have a sugar molecule, that is the aldose sugar, and when it is oxidizes to acid by the mild oxidizing reagent, that is the bromine water, then after there is a decarboxylation. Okay. In the rough degradation, the calcium salt of aldonic acid is oxidized with the hydrogen peroxide. The ferric ion catalyzes the oxidation reaction which cleaves the bond between C1 and C2, forming an aldehyde. The calcium salt of the aldonic acid prepare from the oxidation of aldose with an aqueous solution of bromine, and then adding the calcium hydroxide to react the mixture. That means in first step we have the aldose molecule. This is the chain shortening reaction, that is the rough degradation. Okay. Initially we have a aldose molecule. Okay. In first step, this aldose is react with the bromine water, which is a mild reducing reagent. And as we know, in aldoses, the C1 carbon atom is a aldehyde group, and after the oxidation with the bromine water, this aldehyde is converted into acid molecule, and once the acid is formed, it can be reacted with the CaCO3 that gives the calcium salt of aldonic acid. Okay, and after the formation of this calcium salt, it can be oxidized with the hydrogen peroxide, and after the oxidation with the hydrogen peroxide, there is a ferric ion catalyzes the oxidation reaction, which cleaves the bond between C1 and C2 to form the aldehyde molecule. And okay, and the formed product is less than 1 carbon atom. That means if we take the glucose, then after the rough degradation, the product contains the 5 carbon atom. That means glucose converted into D-arabinose. So this whole reaction is called the rough degradation. See the reaction. Initially we have a D-glucose. Okay. In first step, this react with this mild reducing reagent, that is Br2, in presence of H2O, bromine water. There is an oxidation of this aldehyde to acid group. Okay, that means this CHO converted into COH in first step. In next step, there is a calcium hydroxide is reacted with this acid, and it gives the calcium salt of this D-glucose, that is the calcium D-gluconate. Okay, in second step, we got the product, the calcium D-gluconate. In next step, there is a oxidation with the H2O2, and this fatty zones reduction gives the cleavage of this bond, that is the C1 and C2 bond cleavage, and there is a CO2 released, and the product is formed, which is the D-arabinose. Okay, so this D-arabinose is a 5 carbon sugar. You can count 1, 2, 3, 4, 5 carbon sugar. That means the D-glucose is converted into D-arabinose in this rough degradation. So this is the chain shortening reaction, that is called rough degradation. Our last reaction is the Kiliani-Fischer synthesis. So in this Kiliani-Fischer synthesis, these aldoses, in first step it is reacted with this HCN in presence of KCN. It gives the cyanohydrin molecule. That means initially here we have if we have 3 carbon atoms, then after by the addition of this CN negative, here you can see 1 carbon is increases, and the structure is a cyanohydrin. After the formation of cyanohydrin, here the aldehyde group, that means the carbonyl group, it is a planar structure, therefore it gives a 2 product, that is the 2 molecules of cyanohydrin. Whether it will attack from, it can be attacked from the both side, therefore it gives 2 products. And after the formation of this cyanohydrin, this can be reduced by H2PDBSO4, and this CN converted into this imine as a product. That means here it is a chain lengthen imine. 1 carbon atom is extra in this step, and after the hydrolysis, here it is a aldose molecule we get after this hydrolysis. An aldose carbon chain can be increased by 1 carbon atom in the Kiliani-Fischer synthesis, It is the opposite of rough degradation reaction. The synthesis leads to the formation of pair of C2 epimers. So why this can form the pair of epimers? Because in first step, when we add the cyanide to this aldehydic molecule, this is the planar structure of carbonyl group. Therefore, the incoming nucleophile can attack from the both sides. Hence, we got the two epimers as a product. So you can see the D-erythrose gives the corresponding chain lengthened product D-ribose and D-arabinose. Initially we have a D-erythrose which contain the 4 carbon atoms. In first step there is an addition of the cyanide. So here this is the cyanohydrin. In next step there is a reduction, and after the hydrolysis we got D-ribose where one carbon atom is extra in this structure. That means this D-erythrose is converted to D-ribose. This is the chain elongation reaction. Due to this planar structure, this cyanide can attack from the another side. Therefore, we write OH in this side. After the reduction, we got this, and in last step, after the hydrolysis, we got the D-arabinose. So this is the chain elongation, that is the Kiliani-Fischer synthesis reaction. I hope you understand. Thank you for watching.